Thanks so much for having me here. It's a real honor to kind of speak with the next generation of roboticists and computer scientists. So my name is Jang. I lead the AI team at Humanoid Technologies, and I'll talk about basically how we scale our data engine and use that data to train our generative models for robotics. So the mission of 1X is to create an abundant supply of labor via safe and intelligent androids that work alongside people. And I'll get into how to pack this. So we have two different robots we make. One is called Eve, which is a about 6 foot tall wheel-based mobile manipulator. And we use this in logistics and security. And the other, which is an upcoming model called Neo, is a like 5'6" biped with 5-fingered hands, and we're planning to deploy this in consumer homes. So our offices are distributed both with headquarters in Norway as well as the recent Sunnyvale headquarters we opened. I've joined the team about 2 years ago and kind of built out the AI team in California, where we do a lot of the neural network training and data entry stuff. A lot of the hardware and R&D is happening in Moss, Norway. And then the motor manufacturing happens in Dallas, Texas. So yeah, I don't know if any of you have seen this recent social media video that we put out. Let's see if this plays. Here we go. Great. So this is kind of our most up-to-date capabilities that we can do right now with end-to-end learning on our Eve humanoid. What you see here is basically a bunch of different mobile manipulation capabilities, and everything you see in this video is just one set of weights that is goal conditioned and does all the tasks. So for each of these tasks, we're sending a different goal images, and it just takes in the goal image and its current observation and sensor inputs, and it does the task. Here you have like a kind of contact-rich task where you're wiping a table, and it also detects when it's done wiping, so that it kind of retreats back once it's done. It's the same model as the earlier view. This is again the same checkpoint, and it's just now given a different set of tasks to fold this shirt, and then it'll also do that. It's not like superhuman level, but it's kind of a start. It also has this nice feature where we're kind of baking in the HRI into the model checkpoint as well, where if a human goes like this, the model will know that it has to hand the shirt to the again, the same model is also being used now in our logistics deployments. So here's a task where it's given a goal to kind of pack this box and stuff it with this cardboard coming out of this this dispenser. I think it may do that in the next clip. And so these are all traditionally tasks that are very hard for pick and place systems that are based on like sense, plan, act to plan because of the amount of contact richness that's happening in the task, as well as how like closed loop you have to be with the perception action. And then finally, another recent update is that we've gotten that same model to be able to do diverse pick and place. So you put a variety of objects on the table, and it should be able to kind of pick up the objects and put them in the box. For objects like let's say masking tape, where it's like a donut shaped thing, it's unusual because you have to know to put your finger into the middle of the hole and pick it up, as opposed to like treating everything as like a box that you do pose detection. So yeah, that's an overview of our recent capabilities, and in this talk I'll kind of share how we do some of these things. So first, I'm going to kind of motivate at a very high level, like why work on robots? I think these days AI is very popular. A lot of people want to get into it, and there's no shortage of interesting problems to apply the skill set to. For example, chatbots, generative AI, various assistive agents that control your computer. Maybe people want to use AI to reinvent search. There's tutors, there's coding pilots. There's also AI for like advancing sciences and predicting outcomes of experiments and so forth. So of all these kind of exciting areas, why work on robotics? My take on this is that generally all technology is very good. Technology makes people very productive. And the way that software makes people productive and why so many people work on software is that it really accelerates the productivity of information processing. So with good software, you can like make information processing very efficient. However, at the end of the day, in order to make a wealthy society, you need a lot of goods and services. And so the economy needs a lot of these endpoints where actual physical stuff is done. For example, you need someone to unclog a toilet, you need someone to grow some crops, you need someone to pack boxes so that they can be shipped to customers who buy next day shipping, things like that. Information processing and software specifically cannot unclog toilets by itself. Right? You need like some physical endpoint to do labor or provide services or goods at the in an economy. So software is very much like a coordination. If you have a physical industry where it's all labor and no software and no information processing, you have these extremely inefficient processes where like these people are transporting water with people, and you move water this far, and that's very inefficient. But on the kind of other end of the spectrum, if you only have an economy where everyone's doing information processing, you kind of end up with like consultants and a lot of like general someone is like working on scaling the back end for some architecture for some tax accounting software or marketing thing. Like it's all like very abstract. And here's some pictures from the Fire Festival to kind of illustrate like what happens when you don't have really robust physical endpoints to all the information and kind of soft skills. So I think there's also another trend where all AI software is actually going to converge to looking a lot like robotic software. If you think about, let's say, making a really advanced chatbot like ChatGPT or Claude or something, it's basically an agent that's interacting with a particular environment that is very complex, and it is a person. And a person has many characteristics that are similar to a robot operating in an unstructured environment, such as being unpredictable, being very diverse, and generally just a lot of possible places where it can go. And in order to make this very successful, you end up having to build a lot of the same infrastructure that roboticists build to handle the complexity of the real world, such as perceiving the state of the environment, recovering from failure, knowing when you're done with some task or not done with some task, or even instrumenting something like evaluation for general purpose tasks. The same thing is true for many other kinds of bots that people make. For example, algorithmic trading is like this. It's a bot for interacting with a very large market of other bots that are all competing against it. And then a lot of people are trying to build computer controlling agents these days. Computers are easier to control because it's kind of like a set of bits for which you can be pretty sure what happens when you're manipulating reading and writing I/O. Except if the computer is doing anything non-trivial, like interacting with an external database or interacting with the internet, then it becomes, again, much like robotics, where there's this source of unknown information and entropy that you're trying to interact with and deal with. The engineering problems are also very similar, where when you want to scale these systems up, you end up having to build a lot of the same stuff like logging, time synchronization of your images and your actions or whatever sensor modality you're dealing with, and then your future things that you want to predict. Visualization and introspection also becomes useful. In chatbots, maybe it's more about like introspection around why models make the predictions that they do, but you might also want to analyze the failure modes in the wild of certain models. And of course, the infrastructure, everyone's training neural networks. Everyone wants to figure out systems like to build data engines and improve from interacting with the world, and policy evaluation in general is very hard. So my thesis is that the robotics and research engineering skill set, even if you're not applying it directly to physical robots and actuators, will become a very highly sought after skill set in the future of all software, not just in robotics. And because AI is going to eat a lot of other kinds of software, I think the sort of robotics research engineering mindset is really valuable to have these days. I get this question a lot, which is like, why humanoid robots? Like, why go for the 2 arms and 2 legs? Why isn't this enough or this enough or this enough? So I'll kind of explain. There's a lot of robots out there that try to do bimanual manipulation. Sorry, go back 1 slide. Wait for the video to load. Okay, so here's an example of a non-humanoid robot that supposedly can do mobile manipulation. Let's see if this loads properly. There you go. So this is 2 UR5 arms mounted on a Husky mobile manipulator. And you might think like, okay, with this, I can make a home robot, right? Like, why isn't this enough to do chores and so forth? It's got 2 arms, it can move around, so why is that? And then in research, we're seeing increasingly more systems like this, such as the OK Robot, which is a modification of the Stretch robot, the Mobile Aloha from Stanford, and I forget what the code name for this one is, but it's from CME. So there's this proliferation of pretty capable mobile manipulators that we see. And in the case of Mobile Aloha, you can do quite dexterous things like, take out, unload the dishwasher, cook, and so forth. So again, like, yeah, I get this question a lot. Why can't we just sort of ship this as your sort of general purpose home robot? Why do you need to go full human? My answer to that is that I actually spent quite some time at Google Brain working with a form factor that was basically a static base with an arm attached to a pole. This was the robot that was made by Everyday Robots. And over time, I kind of tried to make it work for like general purpose use cases, but I found that it was inherently very kinematically limited when you want to go to the home. And why this is the case is that when you think about the idealized use case for a robot in home, such as in the previous slide with tiny homes and such, they show you homes that look like this, where you have modified the environment to be admissible to the robot form factor. And if you are thinking about like a home where someone in a wheelchair could kind of get around, that is kind of like what they set them up to look like, right? This is like an ADA compliant home. Most homes look a lot more close to this scenario. This is kind of an extreme example, but most homes do not look like this, they look like this. And this is because humans in the process of occupying a home and just living their life in the home, they end up terraforming the space to conform to their form factor. And it does not really, they don't really think about making it accessible to other form factors. So if you're, for example, an able-bodied person, I'm pretty sure your home is not wheelchair accessible just because you don't optimize your space to be always wheelchair accessible. And what ended up happening in the offices at Everyday Robots was that frequently the robots wouldn't be able to traverse the corridors because the chairs would be in the way, and we didn't have any colleagues who were in wheelchairs, so therefore the chairs were always cluttering the corridor because they didn't obstruct humans that were able-bodied. So I think if you don't live in a house with someone who's regularly using a wheelchair, your house will also not be very usable to a robot that's basically like a wheelchair with an arm on it. Okay, so let's suppose you want to make a humanoid. I think a lot of people in computer science don't understand that like hardware really matters. And so a lot of people think that a humanoid is basically just taking like an arm, multiplying it by 4, and then like attaching it to a torso, and there's your 4-limbed humanoid. So let me explain why that's not the case. This comes down to actually actuation technology. So how many of you have used a UR5 arm? Okay, some of you. So a UR5 arm, it's a great arm for research and manipulation, but it is not a safe robot, even though it's called a collaborative robot. It's not a safe robot because the force, the internal kind of kinetic energy stored in the motors acts essentially like a flywheel. So it's like this fast spinning piece of metal. And if it were to come into contact with some object like a table, it would basically impart a large amount of kinetic energy onto the table. So if I can wind back a little bit, here's an example of a arm that's moving at a relatively slow speed. You see this, right? Like it's kind of going about this fast. And if it moves this fast, it's the energy inside of the arm is pretty large because of the motors that are spinning. So unlike a human arm, the kinetic energy in the joints are very large. And when it comes into contact into an object, that flywheel has to come to rest. And so it ends up being that there is about the equivalent of like a 300-pound person's accelerating on top of you if it kind of makes contact. And that's why these robot arms are not safe. So if you mount these onto a Husky robot and then put this in a home, it's very likely that if it tries to open a door or it tries to pick up an object and it's off by a few centimeters, there's a very high likelihood that it breaks whatever it comes into contact with, or it breaks the edge effector of the robot. And there's also some kind of math involved where if you have a gear, it actually multiplies the inertia felt at the end of your lever arm by the square of the gear ratio times the in terms of the inertia you're feeling from the motor. So when you use certain kinds of design choices in actuation, it can actually make the robot much more unsafe at the trade-off of being stronger. So let's see if this video. Okay, that's an example where it kind of just presses down like this. Yeah, so if someone just goes like this, a human is very safe, but if a UR5 does that, it'll probably squash whatever is under it. And so the result is that most robotic systems deployed in factories and in manipulation settings, they're really careful not to touch anything. So for example, if you're building a grasping system using a UR5 arm, you really want to make as little contact with the object as possible. You want to just barely touch the object and maybe use like a vacuum suction thing to pick up the object. Or if you're in a car plant, you want to make sure that the arm doesn't really actually touch anything with the end effector. And that's why actually cars have panel gaps, is because they don't want to like have the panels come into contact with each other. So this is sort of a joke, but you can see an example here where even if the robot's moving very slowly, if your system is very stiff, it can just like bust through the door, and that's obviously not what you want. You want something that's much more compliant and safe. So what has kind of changed this equation is that there's a new generation of robots coming out now that use this technology called quasi-direct drives, coupled with more efficient motors, which allows you to build systems that are much less stiff, and that allows them to have much more compliant interactions. Some examples of systems that have built this way are like the MIT Cheetah, the Berkeley Blue Arm, and our own Eve. And what this results in is that you have a much more compliant learning environment. So if this video loads, it will show a door opening, and this is from the first-person view of one of our models running, and it's much more compliant. So even if the accuracy of the model is not as good, the hardware compliance helps us with opening a task, opening this door, even if the handle only rotates with 1 degree of freedom, right? Like whereas if you have a super stiff system, the door opening policy has to exactly get the plane of rotation correctly if it's not going to like break the hand or break the door. So good hardware simplifies learning. Here's some examples of Eve being deployed in the household. This is the house of our CEO, and we just kind of shipped the Eve into his house for a month to see what tasks it could do because we want to learn more about our biped deployment use case. And what you're seeing is that the home can be quite cluttered, and that despite Eve being able to do most house cleaning tasks, one challenge is that the base is still quite bulky. So because you can't flexibly adjust the support polygon of the robot, it's much slower to do things like just go around a dishwasher. You can see here that's like we're driving around the dishwasher, and normally a human would do this in like 1 second, but it's taking us like maybe 10 seconds to kind of make our way around the dishwasher to do a simple task. I think this also shows that like legs really help with kinematic reachability. A human would be able to just pick up a dish no matter where they're standing here, but if you are in a wheel-based system, you have to have your base kind of positioned just right to be able to reach objects. And we're kind of learning these lessons more and more that the biped really is the only way to go for general purpose robots.
Is that base non-holonomic?
It is not holonomic base, and a holonomic base would help a lot. But I would argue that even a holonomic base would struggle with, like, for example, if I wanted to like just get something here, it's much faster than having to like traverse. Cool. One other reason that I think humanoids are inevitable is that the hardware is getting much cheaper. So a lot of people say like, oh, a humanoid, it's too expensive. Let's make something simpler. I think the trend is that humanoids will soon become very, very affordable for a lot of people. So if we look at the trend of one arm robots, the Kuga Iwa used to cost about 200K, the UR5 is 30K, the X arm is now 6K, and that cost continues to go down geometrically. The Spot it costs 75K, but you can today buy like a Unitree Go Air for like less than an expensive laptop. And with humanoids, the Atlas reportedly costs about $2 million. The Digit is about 250K. Fourier Intelligence is about 150K. The Unitree H1 for academics is 90K. And then recently Elon tweeted that the Optimus is targeting like half the cost of a car. So let's just say that's like about 20K. So you see this geometric decrease in the cost of a humanoid. And once it gets to this price, it sort of becomes the obvious choice for every robotics researcher to use this form factor. Unfortunately, we're not disclosing the price of Neo just yet, but I'll say that it's broadly following the same trends here, and we expect that it'll be quite affordable for many people. Yeah, I guess one thing I should say is that like safety, capability, and cost are what really matters in being able to get general purpose humanoid robots in the home. So it almost sounds a little bit obvious, but I'll kind of go through how I think about each of these components. In terms of capability, I don't think it's possible to sell a humanoid robot that just retrieves Coke. Like it has to just do a lot of things. It has to pass the butter, do the Coke, like clean your house, reset your bed, like basically a large number of things that would essentially justify the cost of something that's costs as much as a car. So capability really has to be there. And in order to do this, we cannot kind of follow the same autonomy playbook that a lot of other robotics companies take, which is like, let's build this one wedge task and expand the task once customers are paying us for the task. I think it has to be like, from day one, you have to be like ChatGPT, where it just does everything. Safety is very paramount, and this is where our approach to consumer, I think, is quite unique in the humanoid space, is that if you look at the AV industry from left to right, you have the kind of most consumerish case here where you're trying to solve a general drive everywhere problem with FSD. Robotaxis kind of take some like approach where it's like, let's just do robotaxi within one city. And then trucking is like, let's not worry about like the kind of long tail. Let's just solve highway driving and find a well-paying customer. A lot of people thought that autonomous trucking would be the kind of right way to go to market for AVs. But it turns out that that is the kind of part of the sector that has progressed the slowest. And I think it's because the safety stakes are the highest in trucking, where you really cannot make any mistake whatsoever, or many people die. And ironically, it seems like the kind of long tail problem ended up being easier to iterate on because of the relatively low stakes of consumers owning the L2 system themselves. Robotaxis, I think, have done okay, except regulatory stuff tends to get in the way. So in terms of just being able to ship quickly and iterate, it seems like going for the simple autonomy cases is actually not always the best way to do it, especially when safety is sort of a big blocker. We think that the home setting offers us an environment where things are critical for safety, like you don't want to drop something on someone's pet or kid, but it's not so critical that like it would like hold up a production line or like basically customers with a really high, or sorry, customers with a very low tolerance for failure, I think will make it very difficult to iterate. And I think these kind of products require a lot of iteration. One advantage we have on the hardware side is that our hardware is more safe. So you can hug the robot and it's fine. If you have a robot that uses very stiff actuation systems, it's very hard to deploy this. And then finally, for affordability, the hardware has to be mass manufacturable, easy to assemble and repair. And and maybe for unit economics to work out, you want to think about ways for the consumer to help you with data collection, as opposed to hiring a large fleet of operators to help you gather data. So how do we do data? Our data engine is very simple at a high level conceptual point. So we deploy some autonomy. Here's an example of an autonomous door opening task. We identify where it doesn't work. We go and collect data for these scenarios, and then we retrain and recook the model, and we repeat this until the model is good. So this is how we run data engine, and this is basically how any AI company runs data engine. One thing we do that is pretty unique is because we have a end-to-end neural network that does all the control, it means that you can add new skills by only adding data and not necessarily having to run task code. So we have our data collectors actually train the models themselves. So we hire teleoperators who gather data. They gather data for these tasks. But unlike most other robotics labs, they actually go and train the models themselves to figure out what kinds of data help along with the task. And this has allowed us to have a very sample efficient way to learn, because instead of asking someone to gather 1,000 data points, they can figure out the most efficient way to acquire a task without just like taking the marching orders and gathering 1,000 data points. I think when you connect the data collectors to the kind of products of their labor, it results in a much better process for data collection and much higher quality data. So here's some examples of tasks we've trained. And actually all of these tasks are trained by our teleoperators, none of them by the AI team. The AI team just makes the system that trains these capabilities. And an analogy I have here is it's very like farm to table, where you're growing your own data so that you're consuming it, as opposed to like you're growing the data for someone else. That just generally is higher quality files. Here's a plot of how much data we've collected over time. This is the amount of data we've uploaded from our fleet. We've collected probably 1 or 2 orders of magnitude more than this, but this is just the amount of data we've pulled off the robots to train on. And one thing we're working on is like, how can we use more of the data that we are currently not pulling off the robots, because we have a lot of it. And hopefully as we scale the Neo fleet, this will sort of go exponential, and then we'll have a bunch of interesting data engineering challenges to solve in terms of how you centralize all the data in a this distributed fleet, and how you do querying and indexing. I really like to nerd out over the more like boring software engineering data infrastructure sides of these problems, but that's not the focus for this. We also like caption our data with diverse labels for different kinds of activities. And so here's a plot of how many unique text labels we've gathered over time. Around here is when we started doing more like open set text annotation. And then we stopped doing that for a while because we felt like we had enough, but at some point we'll wrap that up again to do more open vocabulary things, and potentially even things like using VLMs to label. Okay, so that's roughly how we collect data. I'll talk a bit now about the different kinds of generative models we train on this data. So in the classical robotics pipeline, you have this stack where to make decisions in the world, you need to go from your sensors to some sort of perception stack. Then you need to plan at a high level what you want to do. Then you need to plan at a medium level what you want to do. And then you want to plan at a low level what you want to do. And those are the task planning, motion planning, and controls, control loops. And then finally, you have some action that you send to your motors and it gets done in the loop. So traditionally, all these steps were designed by hand-written code and expert knowledge with rich theories about how you do each of these things. But in the last 10 years, we've seen this trend where neural nets are subsuming more and more of this process. So of course, in perception, everyone these days pretty much uses deep neural nets to detect what's in the world. But you can also do this for task planning. For example, VLMs are surprisingly good at planning what to do in the world. So you can kind of merge the perception and task planning, at least in language space, into a single neural network. With motion planning, you can also subsume this into neural nets, for example, with predicting end-to-end trajectories directly from the pixels. And this is still in the early days, but I think we're starting to see a lot more literature now where you can actually go directly from sensors to torques, and in the case of like a low geared motor, your current draw is basically just a linear function of your torque. So at that point, you're basically going directly from your sensors to whatever you're sending to your motor drive. And so over time, I expect that a single neural net will be subsuming everything in a data-driven pipeline. And you'll be able to optimize all of these kind of different decision points in a very cohesive and integrated way, just using data. So here's a few different models that we train in this kind of effort to subsume everything into a single neural network. We currently don't have a single neural net. We have a few different neural nets, but I'll go through some examples here. So one thing that I'm pretty excited about is using generative models like a latent image diffusion to predict the future. Here is a current observation of the robot opening a door, and you give it like a natural language command, like please open the door. And then we pass this through some transformer that does diffusion, and it can imagine what happens 1 second into the future. So here on the right, you see the corresponding future 1 second prediction of given this image. And this is a hallucinated image. This is not like an actual image. This is generated from a neural net. Given this image of what it should do in the future, it's a pretty simple task to then compare these two images and decide what the robot should do, because it's basically just comparing the poses between this image and this image problem, right? So you can run a pose detector on these things and recover the pose you want to send. Of course, like you don't necessarily want to move in a straight line. You might want to do something clever. So this is where you could integrate this with a motion planner, for example. And this is inspired by work from Instruct Pix, where it basically gives us an off-the-shelf way to do this. Another exciting work that we're doing is diffusion policies on the motion planning side. So you can think about diffusion policies as instead of a generative model for your images, you're learning a generative model for your actions. Does anyone here know how diffusion policies work? Raise your hand with you. Okay, a good number of you know. So essentially what a diffusion policy is that it is modeling a conditional distribution of your actions given your observations, your state, your goal. And unlike a typical density function modeling task, like using a mixture of Gaussians or something, you might you want to express a richer class of functions. And it turns out you can express this by predicting what is known as a score function over your actions. And the score function is essentially the gradient of your probability, your log probability distribution. So if you have this gradient, you can then kind of march along this gradient to get you something that roughly maximizes this probability, but is sort of sampling from that distribution. So yeah, this is an example. This video is an example of, I think I showed this earlier, but it's the same video, but this is a diffusion policy running on this robot that opens. I'm sure people have questions about the specific details of what's in this transformer neural network, but that's some of our secret sauce. So unfortunately, I can't share those details at the moment. But at a high level, you can think about like the choice of architecture does not really matter too much. What is really important is to get the data right, and then to have a system that kind of is correctly implemented. And then from there, most learning algorithms are very scalable. I would not sweat the details of like what's in here or how you parameterize actions. And one other way that we are doing learning is that we are moving the learning also to the control stack as well. So our Eve is currently balanced using a whole body controller that's essentially solving, is an ICP-based planner. So it's essentially solving this set of dynamics constraints to keep the thing balanced while also reaching where you're trying to go. But we're also moving to a completely learned gate for our Neo. And here's some examples in Isaac that we've been training our Neos to do. And they are essentially conditioned to follow a particular heading direction and maintain balance. And we're planning to extend this also to handle, let's say, like the target poses for hands. And cool. So I'm going to go through a few like FAQ questions in terms of like questions I get a lot, and I'm sure the audience will have some questions as well. And then afterwards, you guys are all welcome to ask questions if I didn't address them. So I get this question a lot, which is like, you know, it seems like there's a lot of people starting robotics companies these days and making robotics VLMs, and it feels like there's this idea in the air that we're very close to solving general purpose robots. How do I feel about that? I think that things are very optimistic. So I wrote this blog post in 2021 about how I think language models are going to like become a very key component of robotics because they provide a very important core generalization for everything. And I think that's come to pass where you can think about robotics as essentially having a big VLM that does most of the heavy lifting in terms of generalization. So understanding the world, reasoning, and so forth. All of that's basically captured in the VLM. And the VLMs, we can maybe at least assume that they're pretty decent at like understanding unstructured environments. So then if you want to solve robotics, there remains this relatively simple problem of converting the manifold of VLM predictions into the manifold of actions you send to your robot to execute. If you can make the transformation from one manifold to the other not very complicated, for example, maybe it's a very trivial mapping from some image space projected into some 3D coordinates, then it should be possible to learn this with not too much data. And if you can kind of graph these two together in the right way, then at a very high level, it seems like this should solve robotics. Of course, there's a lot of like important research questions to solve, like, you know, how do you even evaluate this thing? How do you train it end to end, et cetera, et cetera. But if you really squint, I feel like the main pieces are basically there to get general purpose robots working. Okay, surprisingly, I get this question a lot, which is like, okay, you've trained a bunch of stuff on Eve. Do you plan to transfer the Eve knowledge to Neo as a way to kind of bootstrap the Neo? We expect that because we're trying to ramp up the number of Neos to you know, hundreds of robots next year and maybe even 1,000 if we're lucky. The Neo fleet will be so large that we'll be able to collect more Neo data than all previous Eve data in about a month. And I think this is an example where academia often thinks that like it's not really easy to collect data, therefore you have to solve these kind of cross-embodiment problems constantly. But in real life, it hasn't really been a problem for us. We like are fine throwing away data and recollecting it. It comes down to a matter of cost. And if you're pretty confident in the strategy, we feel that like throwing away data is not actually the worst possible thing. In some ways, it's probably simpler to like not even deal with the problem of how you retarget Eve data to Neo data. It's just, you know, just recollect it. And we've actually recollected Eve data multiple times when we change the way we collect data or like unlock a certain joint that we want to now like articulate. Okay, another question related to the previous one is like, do you plan to train on human video data from YouTube or cross-embodiment data sets for which there are a lot of good data sets these days? I see there's like two possibilities here that could happen. Let's suppose you have like 1,000 robots. Either it's enough to solve general purpose robots or it's not enough, logically. So yeah, like there's two outcomes. In the first case, if it's enough, then you don't really need YouTube. If it's not enough, that sort of implies that like you need internet scale data to really solve robotics and get them to generalize. I don't think other robotic embodiments will get to that scale. So therefore, the only embodiment that gives you internet scale data that's larger than 1,000 robots, 1,000 robots constantly collecting data would be just the full human YouTube data set, right? Like if it comes to pass that 1,000 robots is not enough, the only form factor that matters would be learning from humans. And you can basically ignore all other robots at that point. You should just focus on humans. So my advice for people kind of interested in this cross-robot generalization problem is that just find a way to get 1,000 robots or train from human YouTube data. That's my kind of hot take on this. Okay, FAQ4, we use SIM, RL, offline RL, orientation, blah, blah, blah. We investigate a lot of good ideas. Yeah, we're interested in many things, but I won't be commenting on specifically like what we bet on. How much do they cost? I can't disclose the exact price at the moment, but we'll share them soon. All I can say is that EVA is less than $100,000 and NEO is trending in that direction of like extremely low cost, much less than $100,000, and we'll share more soon. So that's the end of my talk, and I'm happy to entertain questions for another 15 to 20 minutes. Thank you very much. I'm sorry, one more, yeah, I think that was this number here. Yeah, so are you hiring? Yes, I'm looking for mostly FTEs at this point because we've hired enough interns for the summer. But we hire interns on a rolling basis, and mostly I'm focused now on scaling up the team. What I value right now is like a strong SWE and ML skills, able to handle large amounts of data and really full stack things. In terms of like research ideas, I think all the pieces are basically there. So the existing team knows like what ideas to look at and what to scale up. Our main bottlenecks are around like, how do you work with a petabyte of data as if it was just like a local folder on your computer? That's the sort of nature of the problem we're mostly stuck on at the moment. Nice to have is like experience making end-to-end robotics works. It takes some amount of pain tolerance to do that, and so that's nice to have. And yeah, okay, so I'm happy to answer questions.
So when you talk about like looking a little bit into the future using that stable diffusion, how do you account for like novel environments? Because you had it in an office environment, opening like a door. But if I tell it to pick up a banana at a circus, how is it going to picture that, right? Because there's no real basis for that.
Yeah, I suppose you wanted to synthesize a goal image only if it is plausible to do that. Right, so this is given some view, if I'm like looking at this environment, there's a set of tasks that you can ask me for, and a set of tasks that like, if you told me to pick up a banana at a circus, the robot should tell you something like, I can't do that within 1 second, so it will refuse to like generate an image there.
That's fair. I just meant like assuming it's at like a strange environment, right? Like it's already there, but
Okay,
you're asking it to use this diffusion to predict somewhere that it's never necessarily.
okay, so yeah, so suppose you take the robot and you put it in a new home that it hasn't been in before, and you say like, pick up this object. If it sees the object, you could imagine that a very powerful generative model like Stable Diffusion or Dolly or Midjourney can actually do that task because it's seen many examples of picking up objects, and it might be able to generalize to that new environment, even if the input is a different scene.
Yeah.
Do you buy that? I guess it's not a slam dunk yet in terms of what these models can generalize to, but if you believe that like Midjourney can generalize reasonably well to whatever you ask it for, then I would argue that it can probably give the robot policy a good enough hallucination of what success might look like.
That's fair. My fear is just like, if it's in a new environment, it's got to take the data it has at that moment. And it's a question of if it has enough previous images to do that.
There's probably some failure modes where like, if you're in a completely new environment and this particular drawer opens in a way that's non-trivial, like for example, let's suppose it opens this way as opposed to this way, then of course the model would hallucinate wrong here. And so you might actually need knowledge of the environment to hallucinate well. But if we're thinking in a home setting, it's okay if it doesn't work like literally the second you unbox the robot. Maybe after a warm-up period of a week, it like has spent enough time understanding how everything in your house is articulated, and then so it would be able to hallucinate.
So it'll be learning as it's in its own environment.
Hypothetically, yeah, I'll just give you an example.
So I have two questions. One is, what differentiates OneX from like all the other like humanoid companies such as bigger agility Tesla? And the other is, what are some challenges that your company is currently facing?
I'm not going to answer the first one because this talk is recorded. So then as for the second one, I think the main challenge that we have ahead of us is figuring out how to make our policies much more general. So if you see here in the beginning of the talk, I showed some videos of a lot of cool capabilities. It has some signs of life on generalization. It can do, it's one model that does many things, but it won't work super well if you like move the environment to a different location, or you swap the shirt, or you like have a completely different set of boxes, or maybe a different cardboard dispensing machine. So generalization is very fuzzy, and like I'm not going to pretend I know how to define it, but what we want is something wider than what it is now. And that's basically the main challenge we have.
Along that question, do you see the future humanoid industry to be more fragmented or concentrated, and why?
What do you mean by fragmented and concentrated?
I'm assuming means like, do you see it like many more companies popping up, or do you see them like all congregating into like single one?
There are many humanoid companies popping up, so I think that's like a fact.
Mhm.
Um,
He said many players or like Uber, one single platform. Oh, okay, yeah, what I said was right.
yeah, so I would say that in the immediate term, like short term, maybe next 1 or 2 years, it seems like there's gonna be more and more humanoid companies coming in. As to whether they consolidate, hard to predict. Like, yeah, I don't know. You in the green shirt?
Oh, yeah. So you mentioned the advantage of having a biped robot over like a wheeled robot, right?
Yeah.
Do you guys also train your neural nets to sort of optimize for the task? For example, just picking the rear of the dishwasher, why not just optimize it for the kinematics that you currently have or the Eve or whatever?
You can optimize the policy to work around its kinematics. For example, like if you use a stretch robot and I want to like pick up that can, I have to drive all the way around there and pick up the can, right? Like that is one way to like make the task work, but it sucks. Like it's really slow to do it that way. It's much more natural just to like go pick it up. So I think you want to do all the chores in roughly like 1x speed, you have to have a kinematics that's like very compatible with the environment. And environments are, if there's anything I believe strongly about, more than I believe like deep learning, it's that human environments are really terraformed by humans to be only compatible with human form factors.
Yeah, sorry, just a small follow-up. Sure, they're designed for human interaction, but there can be a more optimal way of opening a laptop, let's say.
Okay, tell me, what is that way?
I'm just giving an example.
No, like, give me some examples of where it is more optimal.
I don't know if I knew what was optimal, I'd probably doing it that way, so.
Yeah.
The only idea is that, are you guys sort of figuring out what is the optimal way to do a task with a human robot? Somewhere?
The nice thing about a humanoid also is that from like a design and aesthetic and almost like a product manager standpoint, you don't have to overthink it if it's a humanoid. Whereas like, I've been in no shortage of meetings where people talk about like, what is the task and how do you, what can this robot do with this particular form factor? And I feel like it's kind of a waste of time. You just go full humanoid. If it's cheap enough, like it's a simple decision. You and the
Along lines, you mentioned that hardware is super important if you want to integrate the hardware with the software. But then you also mentioned that if you use throwaway data and pre-collect it for new embodiments or they upgrade the robot hands. Like, are you envisioning, because you think hardware, you want your controller to be so intertwined with the hardware, you think that's scalable to if you want to like update the hand or update some part of the hardware where maybe the whole project might not transfer as well.
So if I understand the question, it's like, if you want to constantly upgrade the hardware, doesn't that create a problem where you have to constantly be throwing away your data? Is that the nature of the question? It is a problem. I would say that at an extremely large scale, if it turns out that you do need like 1,000 years of data to like train a general policy, then you definitely want to be careful of not throwing away data. But at our current scale, we collect more data each month than basically all the previous months combined. So it is much simpler from like an engineering time to just throw away data. I would say that at a much larger scale, you do need to start to invest in ways to like preserve old data. But like, if you think about it from a very general learning perspective, you have a probability distribution, a joint probability distribution over, let's say 10 variables. And then now you want to learn a joint distribution over 11 variables. How do you maximally incorporate your previous like 10 variables with a data set? So now you have data from like a 10 variable distribution and an 11 variable distribution. Like it's a whole research project in itself as to like how you optimally combine these things. And you could just like not overthink it and just pay some more people and collect more 11 variable data. Like, that's kind of how I think. It's an engineering trade-off of like what is the most important problem to work on.
Along
Yes.
those,
Potential use of trying to predict how things might go catastrophically wrong in the next second, rather than just imaging the correct opening of the door. So
That's really funny. It's like Yeah, it's like the robots, like imagining all the ways it could die in the. Yeah, we are currently not doing that, but that's an excellent like suggestion, and like, I think it would be very funny to do it, so we'll probably do it.
From online, so as you're adding more tasks and more data, how do you evaluate the policies and track progress across the tasks as you add more?
It's a great question. So evaluation to me seems like, that's like one of the sort of very big problems that we have, in terms of. Maybe it's even more important than the generalization question that I mentioned earlier. It's like, as you make these general systems, how do you continue to iterate on them? If you have a model that can do 1,000 tasks and you make another model, how do you compare them and so forth, right? So that's a very hard problem. We're tackling a mix of short-term and long-term ways to evaluate things. A short-term way to evaluate things is to have a task for which the metric is not a success number, like 0, 1, because then you need a lot of trials to estimate the parameter of a Bernoulli distribution. Sorry, binomial distribution. Instead, if you can think about an evaluation where the metric is more continuous, like how many times did I open this door and close the door in a row before I failed, that could give you a much better signal in a shorter amount of time. It's not a perfect evaluation because it's only for one task, but if you have a good set of tasks there, it can help you tell the difference between terrible and okay. Then the question is, as you continue to improve the model from like, let's say 90% success to 99% success, or 99 to 99.9, you probably need a completely different set of evaluation technologies to be able to tell the difference between something that's like 99% success rate versus 99.9% success rate.
So actually, that kind of brings up an interesting question, because you have this idea of basically learning all tasks like spread across like thousands and thousands. So you could think of the space of tasks very continuously, a very continuous space, but evaluating them in a discrete sense might like kind of force you into different bins. So
Yes.
when would you think?
So I think the sort of correct evaluation system is not going to be a single methodology for getting everything. It'll be like a whole mix of things that we try to get a holistic sense of how good models are. I would love to have a system that just evaluates on millions of tasks rather than one task, but I would also take one task over 0 tasks. So I guess if you want to build something that's more scalable to thousands of tasks, you either need a very general simulator for which you can easily onboard new tasks, or you need to do something like what Tesla does, which is evaluate in the wild in shadow mode, where they're actually at customer sites and you do A/B testing with different models. There are some drawbacks to both of these approaches. I think it's very hard to do evaluation of a closed loop policy in shadow mode, because you don't know the counterfactual what would happen if you actually took the shadow mode action. It works well for perception, which is what Tesla does for shadow mode, but I think it's incredibly hard to do that for something that's closed loop, because a policy might be very bad only if it takes that action, right? Like, you do that.
How do you plan on handling distribution shifts? So you imagine you see new objects in your home, like a different looking laptop or computer. Do you plan on, or do you think it's something that needs to be handled? Or do you just go about collecting more and more data and constantly training it for?
Yeah, just make your training set look like your test set.
But don't you have to then train a model forever, and it's like a very tricky process because you're always playing this game of collecting new data and you want to make sure you don't forget the old stuff.
There is a finite set of homes on the planet.
But I guess the pushback would be they're constantly changing, right? The homes, the way they looked 50 years ago is very different from how they look now. There's no way to tell how they look. Is it slow enough that it doesn't matter?
I think that VLMs can generalize well enough to homes today where they can solve a lot of practical perception tasks. And that is like an existence proof that generalization to a reasonable degree is not hopeless. And therefore, if you could somehow convert that understanding into a motor action, it seems to be that like you could solve robotics in a non-hopeless way. It seems like somewhat tractable. I think like theoretically you are correct that like you could never observe the full training set, or test set, but there's some, I think, hope from, I think, chatbots and the VLMs that like it's plausible to.
Yeah, I wonder if the robots gonna work under the dynamic environment, because, the action is generated by the diffusion model, but the diffusion model is based on the current situation. But under the dynamic environment, the prediction might be a little off, because there might be some people getting into the way. How would you deal with the dynamic household, for example?
It's a good question. So I would say that in the short term, we're tackling mostly quasi-static mobile manipulation tasks where, you're going to assume that things are not like in rapid motion as you try to manipulate them. And for that case, it's probably acceptable to move at somewhere around 10 hertz. I kind of made that number up, but let's just say that's how fast these things go. For more dynamic tasks, I think there is a very tricky problem as to how you do fast control, but still integrate exteroceptive information, like from vision and so forth. Most dynamic robotic learning work I've seen has been mostly blind policies or policies that incorporate vision at a very slow rate. And I think it's still not clear how you do like blind manipulation or like dynamic stuff, but find a way to get the visual.
I'm curious if like the robots are able to kind of reason about like what task they should perform, because it seems like, for example, if you have like a person working at a factory, they're able to kind of reason like, if I get a general task, there are a bunch of different things that I can do, but it seems like for your robot, you have to like tell it like, from the dishwasher, do this, which can be kind of less useful. If, like, for example, I just want to robot at home to like clean my stuff and like do things like that. So I'm curious. If you do anything like that, or like what the challenges are.
Yeah, by no means have we solved that. So I'm gonna just give a hypothetical way that this could be addressed, but I'm sure this would not work right out of the box. So as I mentioned earlier, the general policy we learned in our recent video is a single model that takes in some goal and then like it does the thing because it has current change. So if you're showing it a picture, for example, in the case of like the hallucinated future image, if you're showing that as the goal, I'm not saying that's what we do, but like, for example, if you did that, the model would be able to see like what a success state looks like and what your current state looks like. And so you can imagine your home robot gets a picture of your clean house and then your current actual house, and then it has to just diff them and then realize the diff.
Does the Eve or the Neo have any type of way to like decipher if they're holding a like high risk object, such as a knife? If you're unloading a dishwasher, would the robot handle like a sharp object or something that's fragile in a different way, especially in a dynamic environment where there's, as you mentioned, like kids running around and someone in the way? I'm curious to know if you would hold the knife differently, if you approach that task differently, and if the model is sophisticated enough to do so.
I think that is very important to do, and we are working on some things to try to address that.
Along those lines, is there a pressure sensor in your manipulator's hands?
The Eve has robotic grippers, which are not made by us. They're just stock parallel jaw grippers. Great product, but no parallel jaw grippers. And then the Neo has 5-fingered hands, and we're looking into various kinds of sensors. Yes. Maybe you first, and then.
Okay, I was wondering, like you mentioned, like kind of like a farm, right? You kind of like try to get like the best data, right? So you need to the robots, so like you kind of like learn some optimal data instead of like just training a bunch of data points, right? So I was wondering, like, what if like because you have a robot fleet, if like multiple robots like learn the same thing, how do you determine like which like data point is probably more optimal than the rest?
The question is, if you're training on a lot of data from different people optimizing their own models.
Like you get like say if you train a policy on like 10 different experiences, but they're all trying to copy or they're all trying to copy the same task, right?
Yeah.
How would you determine like which one's the most optimal like data point you'll choose from to then incorporate into the data?
I guess it's the same problem as what like chatbots face with you have feedback from many different raters and users, and how do you know which ones to train on, right? Which is like a mix of a product and a technical question. So it's the same, I would say like our process for dealing with that would probably be the same as like what OpenAI does.
My question is, how do these kind of robots interact with humans, so human to robot interaction in terms of, for example, I can imagine application of this robot in nursing. It would be like really useful in many places, but we want to make sure that we don't physically stop the patient with the needle, right? So that's also a question about what you talked before, which is stiffness of actuators. So I know like all of these interactions will be really gentle. So how confident are you that, for example, these interactions will be able to happen in the future, or how close the technology is to that point?
It's very hard to guarantee safety when you're holding a sharp. To be honest, don't have a great way to think about how to guarantee safety in those kind of extremely high empowerment situations where you can like easily injure someone. It doesn't really matter what actuators you have at that point. Like a child can also like injure someone with it. So then to me, it seems like at that point, you just need extremely good safety, like base model, almost like a foundation model type thing that just understands safety in a very, very general way. And that would be how we like make sure that it doesn't poke people in shotguns. That's kind of how I would. I'm
think
running
we're-
very
yeah.
short on time.
Yeah, we're gonna-
Maybe time for one more question. Sure, go ahead. Both of you can go, sorry.
Okay, so, how do you decide your go-to-market timing, and then how many hours of robot data are we looking at when you think it's like finally capable? Like, how many hours of data do you think you need?
I would hope that it's something that 1,000 robots can gather, but I don't have a specific count on those.
And like, how do you determine like it's good timing to go to market?
Life is really short, and you should try to go to market as fast as possible.
All right, let's just thank the speaker.
Oh, we have one more.
Okay, one more.
Question was sort of related. You could argue there's sort of like a chicken and egg problem where maybe you need to deploy to 1,000 consumers and do data collection to make a good product, but you need a good product to convince 1 million people to buy it. And with like Tesla self-driving, their cars provide good enough facilities to purchase before they have the smart software. So I'm just sort of curious how you think you could take on that problem when it's like you need to provide enough utility, at the onset to convince them.
It's a great question. It's something we're trying to figure out right now. Most likely, it's a combination of some like minimal amount of autonomy that is necessary to have some value. A combination of maybe like the Tesla, you need some sort of use case that is not dependent on autonomy. For example, like maybe my parents live far away and I want to like tidy the house for them because I'm a good son or something, and I want to like do that by myself as opposed to like hiring a cleaner because I'm an immigrant child and that's kind of the thing that we do, and like so like these kind of use cases that they might crop up, but I'm sure there'll be like many other things. Like for example, if you have a pet and you want to pet sit your own pet at home, that's something else that people might be interested in. Okay, thank you very much.
Thank you.
My email's on my website if you have follow-up questions. I'm sorry I couldn't get to everybody.